Well, in this video, we're still talking about Lewis electron dot structures. We're still talking about some exceptions in drawing them. And this exception is called resonance. So sometimes two or more structures work and are interchangeable. Well, then what? So let's use an example of this, the nitrate ion. Let's draw the Lewis electron dot structure for this, and I'll do it using all the steps just as a good review. First, sum the valence electrons. So nitrogen on the periodic table is 5 valence electrons, plus oxygen, which is 6 times 3, plus I have to add one more because there's one in the upper right-hand corner here, meaning there's one more electron. So 18 plus 1 is 19, plus 5 is 24. So I have 24 valence electrons to work on. Let's assume it's in the right order, and let's do N and bond the O's around it. This is used up 2, 4, 6 electrons. 24 minus 6 is 18 electrons left. So if I want 2, 4, 6, 8, 10, 12, 14, 16, 18, I'd be fine, except nitrogen would not be fine because nitrogen would have only 2, 4, 6 electrons around it. All right, that means I've got to go to a double bond. So let's try a double bond right here. That uses up 2 electrons. I now have 16 electrons remaining, and I could go 2, 4, 6, 8, 10, 12, 14, 16 electrons around it. Well, now I'm good with 8 here, 8 here, 8 here, and nitrogen has 8 around it. I'd put brackets around it like this, and I would have my Lewis electron dot structure. But people are jumping up and down and saying, why did you put the double bond right here? Couldn't you have drawn it with the double bond over here? And you know what? People that are saying that, you are correct. You could have drawn it like this. And still yet there are other people saying, why did you draw that not here or here, but why couldn't you have drawn the double bond to this oxygen right here? And you know what? People that are saying that are also correct, because you could have drawn it this way. So which one of them is correct? Well, sometimes 2 or 3 structures work and they're interchangeable, and we actually draw all 3 and put arrows going between them, indicating it could change from here to here to here. But deeper in, what's really happening is this double bond is rotating from here to here to here to here to here to here, and it resonates between all 3 places. This resonance, when measured for length and strength of bonds, actually shows that this bond, and this bond are all equal in length and strength. And since there are 3 bonds with 3 areas to bond, with 4 bonds to go around, each one of these bonds is like 1 1/3 bonds between each. So this is like a bond and a third, this is a bond and a third, this is a bond and a third. How do we illustrate that? Well, we draw all 3, we put arrows in between, and we know that this double bond resonates between them, and it's like 1 1/3 bonds strong. So since all 3 work, the double bond is said to resonate or rotate between them. The fancy word is that these molecules have resonance, and the bond length and strength is a fraction. It's a blend of all of them. So it's like 1 1/3 bond strength here, 1 1/3 bond strength here, and 1 1/3 bond strength here. I have one more resonance example to show you, and it's really nice to show it in the textbook because it's a tricky one to draw. It is the molecule called benzene, and the molecule benzene has 6 carbons and 6 hydrogens. Ch8.6 is its molecular formula, and if you look at it in the textbook, you can see that it has C6, and 1, 2, 3, 4, 5, 6 hydrogens. Take a moment and draw one of the possible structures right here. Notice how the double bond rotates here. It's every other carbon. But yet I could also draw this as a double bond on the top, and then a single bond on the side, a double bond here, a single bond here, a double bond here, and a single bond here, and then I would have carbons connected to hydrogens in each of these spots. And these double bonds could rotate. Once again, this is a resonance structure, and the two interchange between one another. Sometimes you'll see a space-filling model like this, and this structure has these dashed lines indicating that the double bond rotates between them. This is called an aromatic organic compound. That's because it's a cycle or a circle type compound like that. It's a regular hexagon of carbon atoms with a hydrogen bonded to each one. The dashed lines represent the blending of the two equivalent resonance structures. Now, since this is a lot to draw when you draw a benzene, lots of times there's a shortcut to drawing this. Shortcut to drawing this is just to draw a hexagon. And then you can draw the double bond, double bond, double bond, rotating with the double bond, double bond, double bond. Or even an easier way is just to draw a hexagon with a circle around the middle, meaning that those double bonds rotate like this. In benzene, the rotation of those bonds is a lot like the mixing of the colors, where you can say this double bond and this double bond and this double bond all mesh together to give you like a bond and a half at each spot. Good luck with your resonance structures.